Okay, sorry, that video is going to look weird that it just cuts to this, but I got kicked out of that classroom. All right, so back to what I was saying here. If we rotate this all the way around, right, if I let theta vary, I'm going to swing all the way around. Let me zoom out a little bit. So you can see this point is going to come all the way around if I let theta go from 0 to 2 pi. And then if I change my angle phi just a little bit, so I rotate that point down a little bit more and swing my theta all the way around, and then just continue to do this, okay, let phi come down more, and even I can let phi go down below the xy plane and swing around. What I'm going to get in the end, all those points, will form a sphere. So this might make a little more sense here. So notice if I change phi, I'm going to just move up to some point on the sphere, change phi, going to be up here some point on the sphere. And then if I change theta, it's going to swing me around the sphere. So all those points will create a sphere, which is why they call these spherical coordinates. So we do have some restrictions. The theta has to be between 0 and 2 pi. So when you're pointing, initially you're up, phi can come down, or phi can go between 0 and all the way down, straight down, which would be pi. So phi is between 0 and pi. That's this. And theta, which is this angle, can go between 0 and 2 pi. So you can do a full rotation there. And then rho can be, of course, greater than or equal to 0. That's the radius of the sphere. All right, now, if those are the coordinates, then here are our conversions. If we want to go from Cartesian over to spherical coordinates, it's a pretty complicated conversion. There's your x, your y, and your z conversion. So just remember that when you go to spherical, that's your replacement. See, with cylindrical, we just did r cosine theta, r sine theta for x and y respectively, and z just stayed z. But for spherical, we have those. Now those look like it might make it more complicated, but it turns out that a lot of these problems can become much easier by going to this coordinate system. Now here's another example of a spherical region. So let me see if I can kind of show you this. I'm going to show it to you from the back side. So what we have here is I've taken my phi and I have restricted it between two constants. And I can use, let me see, hold on. I have it written down here. C and D, alpha, beta. Okay. So if I restrict my phi between two constants C and D, my theta between alpha and beta, and my rho between A and B. So let me explain that with this picture. Now we're looking at this kind of from the side. So what I've done is I've said, all right, look, I'm going to start pointing out up the z-axis. This is going to be phi. What I want is to restrict my phi between two constants. So let's say that's c, and then I can let phi be anything between c and all the way down to d. So that gives me all of this swing of angle here. But my theta is between alpha and beta, so my rotation, once I swing down, I have to start rotating around like this. If I restrict my theta between alpha and beta, then you can see this would be alpha, and then swinging through here would be to beta. So I'm allowed to get phi between C and D, phi, between C and D, and then theta is between alpha and beta. And then I let my rho be between A and B. So rho is how far out I walk. So if I'm here, I can swing down, I can swing anywhere in here, and I can walk out only between A and B. So this would be A. So the distance from the origin to any of these points on this little surface here is A. And then anything on that outer edge would be a distance of B, and it's everything in between. So what you get is this weird looking solid shape, three-dimensional solid, which is really like a spherical rectangle. All your variables are stuck between constants. Now I can adjust this, which I will, just to show you some different variations. Let me make this a little smaller so I can see what I'm doing. How about I let my radius go from the origin out. Okay, here's another region. Bring up a little bit there. And let me just swing this around so I can see what I'm doing. Okay, what I've done here is I've restricted in spherical coordinates. I've drawn a ball, a solid ball, but I'm just looking at the first octant of that ball. And let's say it has a radius of, let me change the radius here to about, let's make it 2. So I'm close enough, 2. All right, there we go. So there's that. That's a solid ball, but I'm just looking at it in the first octant. So let's talk about my restrictions. If I wanted to draw that, my restrictions would be, let's see, so phi is the angle from here down to the x-axis, which would be 0, right, all the way to, what, a quarter rotation, so that's pi over 2. So my phi is between 0 and pi over 2. And let me just double check that I'm recording right now. I don't want to go through all this. I kind of got scattered there when I had to evacuate that room real quick. All right, I'm good. So phi is between 0 and pi over 2. And then my theta is the angle on the ground here. And again, I am only in the first octant. So if I look at it from the top, I can see the angle. This is the x-axis. I'm swinging over towards the y-axis. So that again is a quarter rotation. That's going to be pi over 2. So theta is between 0 and pi over 2. And then finally, rho is the radius. Excuse me. Excuse me. And it's all the points from the origin out to 2. So it's everything in between. So my rho is bounded between 0 and 2. So that's what that region would look like. Now let's just see what would happen. What if I change it so that my rho actually only goes from, instead of 0 to 2, how about 1 to 2? So I'm only allowed to include points that are distance of between 1 and 2 from the origin. So I would have, let me change this to about 1. See how close I am to 1 here. Pretty close, close enough. So look what happened here. It's like we carved out this region inside, right? So it's like we scooped out everything that was, we scooped out a ball, a portion of a ball in the first octant, right, that had a radius of 1. So that's what these restrictions on phi, theta, and rho would give us that spherical region. So you can see this region is very different than, it's a lot different than a cylindrical region is, and it's different than a Cartesian. I mean, in terms of it's easier to define this. It's very easy to define that region in spherical compared to imagine trying to define that in Cartesian or cylindrical would be much more challenging. So whenever we have regions like this that we're trying to integrate over, it's natural for us to want to switch to spherical. All right, now let's talk about the actual setup of the integral. So if you have a region E, and you have these restrictions on theta, phi, and rho, then our triple integral will turn into, okay, so this is our conversion. We're going to go from alpha to beta, and I made it too big. Let's go 150. Okay, it'll go from alpha to beta, and that'll be our restriction on theta. And then it'll go from C to D, and that'll be our restriction on phi. And it'll go from A to B, and that'll be our restriction on rho. And then all you do is you go in the function, you replace the x with, remember what I said, we have to turn x into something ugly. Here it is. All x's will be replaced with this. All y's replaced with this. all z's replaced with this. And then we have this very important rho squared sine phi. That is kind of like, remember when we did polar, and even in cylindrical, we always had to throw an r in there. Well, anytime you convert to spherical, you're going to have to throw a rho squared sine phi. Always remember to put that in when you go to spherical. In the next section, 12.8, I'll actually talk about where that comes from. All right, so I think it's time for us to do an example. So let's do the triple integral of e to the square root of x squared plus y squared plus z squared with respect to volume, where e is the region in the first octant between the spheres of radius 4 and 9. So what I have here is I'm looking in the first octant. Only in the first octant. I have a sphere of radius 4. So let's say here's 4, here's 4. And we know we have a sphere. So it's going to be, that's the first, just the first octant portion of that sphere. And then we have another sphere, which has a radius of 9. Up here at 9. So it's going to go like this. Like that. And it's the region between the two. So this is exactly, well, not exactly, but very close to this picture I showed you a second ago, right? Except in the picture I showed you, the radius that we had was 1 and 2. Here it's 4 and 9. So it's this picture with that scooped out piece. It's the stuff in between. So we should be able to define that region pretty easily in spherical coordinates. So in spherical, we're going to have that phi is between 0 and pi over 2. That theta is between 0 and pi over 2 also. And this time rho is stuck between 4 and 9. And now what we do is we try and set up this triple integral with spherical. So I look at this triple integral over e, and now I know it's going to be triple integral. I know I'm going to have these restrictions. I'll worry about the order in a second. E to the square root of x squared plus y squared plus z squared. Well, remember earlier when I had this note up here that there was a nice equation right here. Rho squared is x squared plus y squared plus z squared. So if I take the square root on both sides, right? This inside piece right here is x squared plus y squared plus, x squared plus y squared plus z squared. That is rho squared. Take the square root, you just get rho. So when I convert that to spherical, that's just going to be e to the rho. And then because I'm switching to spherical, I have to put in that special thing, which is rho squared sine phi. And then my order of integration doesn't matter because these are all constants. So I'll go d rho, d phi, d theta. And then my limits of integration here, 0 to pi over 2. It's my restriction on theta. Phi, 0 to pi over 2 again. And then rho goes from 4 to 9. And that's the integral that I need to do. All right, so if I was going to do this, I'd first integrate with respect to rho. So remember, sine phi is going to be a constant here. I need to integrate e to the rho times rho squared. And to do that, I'm going to use integration by parts. So I think at this point, I'll leave you to this to take it the rest of the way, because we've done triple integrals already. This is really just a matter of converting to spherical, making sure you get all the pieces of the integral set up properly. Yeah, I'll let you have that. All right, let's look at the next example. Oh, well, actually, that's the work for it. Don't worry about that. And then that's the homework assignment. You know what? Since that's all I have to talk about with this, and there's some more videos with examples, let me go ahead and work this one out. I'll go ahead and do that. So I want to do the integral of e to the rho squared d rho. And I know that I have a sign phi here, but I'm going to ignore it because it's a constant. What I would do is I would set up integration by parts. I let u be equal to rho squared. I'll let dv be equal to e to the rho d rho. And then du is 2 rho d rho. And then v would be equal to e to the rho. So by the formula for integration by parts, this will turn into u times v, so rho squared e to the rho, minus the integral of v times du. So notice I have a 2 there. 2 rho e to the rho d rho. And I can pull that 2 out. So I'm done with this for now. Pull the 2 out. Rho squared e to the rho minus 2 integral rho e to the rho d rho. And I have to do integration by parts again. So u is going to be rho. dv is going to be e to the rho d rho. Du is equal to d rho. And v is equal to e to the rho. All right, so now what we do is this piece right here, which is just this right here in brackets, is going to turn into this times this minus integral of this times this. So I'm going to try and write that over here. I have rho squared e to the rho minus 2 times, in brackets, rho e to the rho minus integral e to the rho d rho. And the antiderivative of e to the rho is itself. So this just becomes rho squared e to the rho minus 2 times rho e to the rho minus e to the rho. And then I can distribute. So going back to this triple integral, here's what I know. This is equal to integral 0 to pi over 2, integral 0 to pi over 2, and then that inside piece, the antiderivative of this, is all of this. I'll distribute the 2 through in a second, but remember I had to assign phi there. So it'll be, I'll just put the sine phi here, sine phi times e, so rho squared, e to the rho, that's this, minus 2 rho e to the rho, and then plus 2 e to the rho. And I'm evaluating that from rho equals 4 to rho equals 9. And then I still have d phi d theta. So I've got to replace all my rows with 9 and then all my rows with 4 and then subtract. So let me try that. This is going to be integral 0 to pi over 2, integral 0 to pi over 2. All right, let's plug in 9 for rho. I'm going to have sine phi times, all right, 9 squared is 81, rho, e to the rho, but rho's 9, so e to the 9th, minus, let's see, 2 times 9, 18, e to the 9th again, and then plus 2e to the 9th there. That's what I get when I plug in 9. Then minus, again, sine phi, and then plug in 4. So 4 squared, 16, e to the 4th, minus 4 here, we get 8, e to the 4th, and then plus 2e to the 4th. All right, d phi d theta. All right, this should simplify a little bit. Integral 0 to pi over 2, integral 0 to pi over 2. All right, sine phi. And then, let's see, 81 of these. 81 plus 2 of them is 83. So 18. 83 minus 18, right? 83 minus 18 is going to give you 65. So we get 65 e to the 9th. I'm going to write it this way. 65 e to the 9th sine phi minus over here, you get 16 of these minus 8. That's 8 of them plus 2 is 10 of them. So 10 e to the 4th. 10 e to the 4th sine phi, like that. And then d phi d theta. All right, that looks okay. Now we integrate with respect to phi. Excuse me real quick. Okay, so we're going to integrate now with respect to phi. Notice also that 65 e to the 9th minus 10 e to the 4th, these are both constants. So what I could do is this. I could just factor out a sine phi like that, right? I'll move it over a little bit. Factor out that sine phi. That'll be a little bit nicer to integrate. Just be one integral to worry about, one antiderivative. So like that. And now antiderivative of sine of phi is going to be negative cosine phi. So integral 0 to pi over 2 times negative cosine, well, yeah, cosine. It's going to go a little faster, but I'll just do this. This is all a constant, so it just came along for the ride. I'm evaluating this from phi equals 0 to phi equals pi over 2. Then d theta. So let's talk about what cosine, let's plug in pi over 2. Cosine of pi over 2, right? Cosine of pi over 2 is 0, right? So that just zeroes out, the whole thing zeroes out. And then we plug in 0. So I'm getting 0 when I plug in pi over 2 minus, now let's plug in 0. Cosine of 0 is 1, but then it's negative. So it'll be negative 65 e to the 9th minus 10 e to the 4th. And then I'm going to integrate that with respect to theta. So all that happens here is that this minus and minus become a plus. The 0 doesn't matter. So it's really just this. And you're integrating it. That's a constant, right? So you're integrating constant with respect to theta. We should just get that number, 65 e to the 9th minus 10 e to the 4th theta. That's the antiderivative of that. From theta equals 0 to pi over 2. And of course, when we plug in 0, we don't get anything. But when I plug in pi over 2, it's all of this times pi over 2. So the answer should be 65 e to the 9th minus 10 e to the fourth, all of that times pi over 2. And that should be it. Now, I'm going to double check that because I think I did do that with the computer. Yeah, they went in and simplified it a little bit, but this is the answer right here. So if I take this and distribute it to each one of these, I'll get 65 e to the 9th pi over 2 minus when I distribute here, the 10 and the 2 reduce out, you get 5 e to the 4th times pi. So that answer matches this one, so we feel good about it. That's basically it. Now, for your homework, again, look at those problems that I had assigned there, and you'll get some practice. The difficulty, I think, most of the time is just first getting the correct region, all right? So you'll see in the homework how that works out. And that's it. That's all the notes I'm going to give you for spherical coordinates.